talk is about predictability limits in recommendation. We will be talking about it in session-based context. Session-based recommendation is the scenario where we assume that we don't know anything about the user except the current actions in the current user session. So there might be some interactions with some items, and we would like to predict or recommend an item. In the following discussion, we assume that we will have an incomplete session, a sequence of items, and the task is to predict the next item. And additionally, that we evaluate algorithms by prediction accuracy in this task. The questions we wanted to investigate in this paper were first, what are some of the dataset-dependent features that affect or more specifically limit performance? And we were very much inspired by an earlier paper that came out last year. It included the results for 14 algorithms over 9 datasets. The purpose was to establish a common platform for evaluation, so it is a very welcome effort. The benchmarks themselves included some surprising results. There were some trivial algorithms included as baselines, and those trivial algorithms did well, so we wanted to look into that. Additionally, we know that our datasets have regularities. For example, human habits, personal preferences, maybe fashion trends. This allows us to predict and recommend. On the other hand, there are many unknowns that we, the recommender system builders, have to cope with. In practice, we can model these unknowns as uncertainty or randomness, and we have mathematical tools to numerically measure that randomness as predictability. We define predictability as the probability that the recommender will correctly predict the next item given an incomplete session and our previous knowledge. So the best way to understand probability here is to imagine that we're doing a lot of tests, and this is the average ratio of tests that will succeed. On to results, algorithm design. With trivial algorithms, there are simple ways how they find the next item to predict. We can look at individual test cases and the training data for a given training test split. And this allows us to find all the test cases that are impossible to predict correctly for this given algorithm. And this gives us the upper bound on predictability. We included 5 algorithms here, just very briefly. Markov chains and association rules do pretty much what you would expect them to. Sequential rules emphasize sequence, one item following another in the training data. And it allows to recommend items that do not immediately follow the current item, so there could be some items in between, and there is a gain weight associated with that. And then there are the k-nearest neighbors methods, where we find interesting sessions, either by looking for a specific item or sessions similar to the current session. This graph shows predictability limits for 4 algorithms. We compare them to actual algorithm performance using the hit rate at 20 metric. The horizontal axis is the datasets. You can see that there are 3 algorithms shown. The association rules and the item canon have the same limits, and we chose association rules for display here. The shaded parts of bars are actual benchmark results from the paper we referred to earlier. The clear parts of the bars are whatever gap remains to the upper bound of predictability we determined in our paper. Additionally, we show the state-of-the-art result, which is the best result by any algorithm using the exact same training test split methodology. There are two key observations here. First, if you look at the left side of the graph, there are music datasets there, and the fifth dataset, the retail rocket e-commerce dataset. You can see that the limits are below state-of-the-art results in many cases, meaning that for many of these trivial algorithms, there is a theoretical limit that is already below some result achieved by another algorithm in the benchmark. Again, if you look at the left side of the graph, there are sparser datasets there, and the right side of the graph has denser datasets. And you can see a very similar dataset-dependent behavior for all of those algorithms. So, sparsity appears to be a problem here, a limiting factor. When we have abundant training samples for a unique item dataset, then the type of limit that we determined here doesn't appear to be as important. There was a fifth algorithm that we looked at, session-based nearest neighbors, which has a completely different behavior. The limits are higher, and most importantly, if you look at those sparse music datasets, out of the mix, 30 music are now playing, the limit is about 90%. So session-based nearest neighbors is not limited in the same way. Very briefly about the predictability limits that are determined by randomness. So this graph shows the upper bound on predictability and the best known benchmark result using the iterative one metric. You can see that the limits we determined are roughly around 60% for most of the datasets. Fortunately, this result was perhaps a bit less immediately applicable than we had hoped for. One reason is that this upper bound is ways above the current results. So it is difficult to draw an immediate connection there. Another thing is that the iterative one metric is important if you really care about the top spot in your ranked list of predictions, or if you really need to get your next prediction right. In summary, we looked at some trivial algorithms. Despite their good performance benchmarks, we really numerically established that they suffer in conditions of data sparsity. To put it very crudely, for example, sequential rules is maxed out, might perform well, but no amount of parameter tweaking will improve it. On the other hand, session-based k-nearest neighbors is not limited the same way, and it is a very interesting algorithm then to study further in session-based recommendation. Predictability limits due to randomness would be interesting to extend in various ways. For example, to other metrics that are frequently used. An open question remains whether it is possible to do a similar approach with other algorithms that are important in recommendation and use say matrix factorization and neural networks. So thank you, and I will be happy to take your questions and comments.